Welcome to 15-Minute Tech Talk. Thomas Dimitrovich. We're going to be talking about a 75 kVA transformer, very common size transformer. So I'm going to hit what you may or may not understand about transformer applications. And so please don't forget to subscribe. Hit the thumbs up button if you can, if you like it, and don't forget to subscribe. And also, there's a little bell when you subscribe. If you hit the bell, when I go live like this at any point, you will be notified. And so I think that you may or may not like that, but hopefully you do. So let's get set and let's get ready to get this done. All right. So we got a setup, which is there, right? So now I got the PowerPoint queued up. And if you've ever been to one of my 15-minute tech talks, you know that over here, I put 15 minutes on the clock. I'm going to get through this description of sizing the primary and secondary overcurrent protective devices, primary and secondary conductor sizes on a 75 kVA transformer. And if there is some discussion, there is. I don't even know if I'll get anybody online live because I'm not advertising these things. And that might be for a reason. So here we go. 15 minutes on the clock. And we're ready. All right. So 15-minute tech talk on transformers. 75 kVA. So here what I have is an actual nameplate from a transformer. The important information that I'm going to need is obviously the kVA size, and it's right there listed on this transformer, and I can show that to you nice and a little bit closer, maybe a little close-up of that. So there's my 75 kVA for my transformer. The other thing that I am going to be interested in, obviously, is my voltage, right? So I need a primary and secondary voltage. In this case, this is a 480 volt delta to a 208 volt secondary Y configuration, 120 volts line to ground, line to neutral. And I'm going to need that information. Why? Because I need to determine full load amps on primary and secondary, and I need kVA and I need voltage to get that done. Now, the other piece of this pie, and I did this, I did a 30 kVA, I think it was, transformer the other day. That's also out there. And if I can, I'll link to that 30 kVA transformer up above. We'll see if I can make that happen. All right, so the impedance of this transformer is 5.06%. And that the transformer impedance is going to be important for me to determine the available fault current on the secondary, the maximum infinite bus calculation of available fault current on the secondary of this transformer, so that I pick the right interrupting ratings for those secondary overcurrent devices. The interrupting ratings on the primary devices are going to be driven by the available fault current coming from the upstream source, which could be anything. So it's outside of what I'm going to get into in this session on transformers, because if you really think about that primary overcurrent protective device and its interrupting rating, the available fault current at the terminals of that device, I've got conductor upstream. I may have motor contribution coming from upstream. I might have, a really good stiff utility source or whatnot. So it's not what I'm here to talk about. Suffice it to say that that primary device has to be able to interrupt the available fault current at its line terminals. So I'm going to work through picking overcurrent protected device number 1 and 2, conductors 1 and 2. I'm not going to be worrying about device number 3 down there in the bottom, because that's just not part of my job at this point, not part of this program. Now, my steps include first calculating the full load amps and applying the multiplying factors from the National Electrical Code. I don't pick the conductor right off the bat, and the reason is because selecting your overcurrent protected device is the driving factor, and it's not about what size conductor you have. It's about how much full load amps you have and what your inrush currents are. So you don't make the mistake of picking the conductor first and then picking your overcurrent protective device. You have to pick that overcurrent protective device based upon the tables, and possibly we're going to show some time current characteristic curves as well. We have to be mindful of the inrush current. So you calculate your full load amps, you add your multiplying factors, you select your overcurrent protective devices, then you establish the overcurrent protective devices will establish the ampacity of the conductors that you need, and then you select those conductors based upon the conditions of use. Chapter 3. So the equation we're going to need, this is a three-phase transformer. So it's this first equation right down here at the bottom. And you're going to see an extra 3 in this equation because me and the square root of 3 never get along. I go to parties and square root of 3 stays at home, or the square root of 3 goes to parties and I stayed at home. So I mind all of my numbers here. If you look at that equation for full load amps, you're dealing with a three-phase transformer. So the first step is to get it to a single-phase transformer. So it's kVA over 3 gets me a single-phase kVA. My secondary three-phase kV, which I probably should put kV three-phase there. kV three-phase, to get to single-phase, I have to divide that number by the square root of 3. And because it's in the denominator, the square root of 3 goes to the numerator. So that's why you've got kVA times square root of 3 over the kV. Now, square root of 3 over 3 is 1 over the square root of 3. So in many cases, you'll see just kVA over the square root of 3 divided by kV. But I am anal retentive when it comes to that square root of 3. So that's the way I roll. All right, so first step is I'm going to calculate the secondary full load amps. On this transformer is 208.2 amps based upon 75 times the square root of 3 divided by 0.208, which is 208 volts divided by 1,000. So I just take care of that right off the bat, and it's 0.208 kV. And that's your line-to-line voltage. So my secondary current, full load amps, is 208.18. Now to get the primary current, I could take 218 times 208 volts and divide that by 480, and I would get my 90.2 amps. Or I can plug those numbers right back into the equations and get 90.2 amps. So instead of 0.208 in the denominator, I'm using 0.48. So now I know my primary and secondary full load amps on this transformer. 90.2 is primary, 208.2 is my secondary. So I've done step 1. Now I have to apply the multiplying factors. And I go to Article 450 because that deals with transformers. And I use 450.3b. I don't go to 450.3a. Why? Because A is medium voltage. B is less than, or 1,000 volts, 1,000 volts and less. Remember, we moved that 600 volts up to 1,000 volts, I think it was a couple cycles ago, maybe last cycle. No, 2 cycles ago. In any case, this table is going to give me my multiplying factors, and I know that I'm going to be putting primary and secondary protection. Again, to use that first row at 100, even if I use 125% for my primary overcurrent protected device, it is very rare that you will not have a primary overcurrent protected device on the secondary of that transformer when you have a panel board downstream. I'm not going to go over those, and maybe I will at some point specifically focus on that, but you're back in Article 240 and you're in 408 for the protection of the panel board and the tap rules in Article 240. So secondary transformer, secondary conductor rules in 240. So in any case, I am going to demonstrate the use of 250%. I will also give you an example of 125% on this transformer. Now, so if I look at the selecting overcurrent protected device number 1, so that's the primary. I've still got 7 minutes to go. I'm doing pretty doggone good. So 225, if I take 90.2 and I multiply that by 2.5, I get 225.5 amps. I can't go, because I'm at 250%, I can't go to the next higher. I've got to come down to the next lower. In this case, I'm going to say that my maximum size primary overcurrent protected device is going to be 225 amps. The only time I would probably get into 225 amps is A, if I want to push that transformer really hard, I could possibly, again, reduce the life cycle, etc. Or B, if I'm selectively coordinating through that transformer. Selective coordination through a transformer, which I do have a video that covers that, could push that primary overcurrent protective device up to much higher than what you would probably feel comfortable in a normal application. Now, the minimum size overcurrent protective device on the primary is going to be driven not by multiplying factors. It's more so going to be driven by the inrush of the transformer. So a 1.25, again, is a common multiplier. And if I use that, I get 112.5. Now, I've talked to a couple engineers. I had one person tell me, I had some, let's just say, I had some good discussions with one person. It was a heated debate with another individual, very logical, and as a matter of fact. So the one design engineer that I talked to said they would typically you would see about 110 amp on the primary of that of this device. They probably would not go, they would definitely not go to 225 in a normal application, but you'd probably see about 110 amps on the primary. I'm not driven by any specific number. I just can't go more than 225 amps. So I just selected 100 amps. So I got 225, and I'm going to see if I can get 100 amps to work. So that's the overcurrent protective device number one, and I would say that's my range, anywhere from a 100 amp breaker fuse to a 225 amp. And when you're in that 100 amp, you better be mindful of the inrush current. Because you're gonna, and we're gonna look at some of the time current. Well, let's take a look at a time current characteristic curve. This is a 225 amp thermal magnetic circuit breaker. Now, also you'll see that I have the inrush current marked there, and I believe that's about 12 times. I was just on a call this morning, and one of my application engineers within Eaton says he'll typically use at these size dry type transformers around 8 times for inrush. You can sometimes get that information directly from the manufacturer. I used 12 times in this case. I probably could have, and maybe could arguably should have done the 8 times as well, but I didn't. So, but in any case, that's around 12 times your full load amps from an inrush perspective. You'll notice that this circuit breaker is on a primary, so it's going to provide short circuit protection of the transformer. It does a pretty good job of doing that. You might get some people say, well, hey, Tom, you're in that damage curve of the transformer. But again, be mindful that the overload protection is going to come from your secondary main overcurrent protected device, not necessarily from your primary overcurrent protected device. That primary device is going to be there for short circuit internal faults within that transformer. Your overload protection is going to come from the secondary. Now, this is an electronic trip unit, 225 amp circuit breaker. I'm at 3.5 minutes, still doing okay. 225 amp electronic trip unit circuit breaker. What's nice about the electronic trip unit is that knee that you're looking at right there. And you might say, well, why, Tom? The previous slide, I'm getting the job done. That's a standard thermal magnetic breaker. Why would I want to add more money to put electronic trip unit in this application? And I'll tell you why. You've got to be mindful of the incident energy downstream. And I didn't speak to it on this slide, but look at the difference. For the secondary panel board, the incident energy for the secondary panel board on this transformer is going to be driven by this primary overcurrent protective device, and you've got to be mindful that there is a transformation of currents that go on because the transformer doesn't cease to do its job during a fault, right? So that primary overcurrent device, in this case, 7.02 calories is based upon a 2-second clearing time because that primary, the fault current, the arcing current, that secondary arcing current, 1.3, so that's 1,300 amps. When I say 1.3, that's 1.3 kiloamps. So 1,300 amps times 208 divided by 480 is 563 amps. The primary device during an arcing fault is only going to see 563 amps. That's going to take at least 2 seconds, probably more than 2 seconds, but you get the 2-second rule in 1584. When I do this, now I am limiting that secondary arcing current to flow no more than around 0.2 seconds. just about 0.2 seconds. And if I did my incident energy calculation, I can knock that incident energy down to 0.69 calories. Your electrical worker will thank you for that if a problem occurs. So the electronic, and that's just that's short time delay. Just imagine if you put the arc reduction maintenance technology on that, you'll knock it down less than 0.69. It'll be a and gun, done and gone, gone and done, whatever. So you do provide additional protection. You'll notice I'm providing a lot more protection for this transformer, but again, I've spent a little bit more money on electronic trip unit, but it's going to produce less damage to your equipment, and it will put your electrical workers in a lesser rated personal protective equipment, which will help them feel more comfortable. They'll be lighter, and they may be even safer working in a lighter PPE. Now, I lowered the overcurrent device on that primary down to 100 amps. And look, it squeezes by. I had to get an adjustable instantaneous. Other 100 amp and even 110 amp breakers had a very hard time with that inrush current. Now, if I did 8 times inrush, I would probably have a little bit easier of a time. But again, some breakers at 100 amps or even 110 amps are really pushing it close. But look, I put a smaller overcurrent device and I get the same amount of energy, 7.02 calories. Why? Because 500 and some amps is much less than the instantaneous pickup, even of that 100 amp thermomagnetic circuit breaker. I did a 100 amp electronic trip unit and voila. Now, you'll notice the short time delay isn't as fast on this one, so I get a little bit more incident energy. But the moment you get an electronic trip unit, if you specify this, talk to our application engineers in the field, there's a very good chance you can get an arc reduction maintenance switch, and I highly recommend an arc reduction maintenance switch on the primary of any transformer that you install for your electrical worker who's going to be doing work on the secondary of that transformer. And now, and you know what, I'll just say that the secondary overcurrent protected device, there is a maximum number that I can use based upon the National Electrical Code, and here it is. Secondary protection shouldn't exceed 125%. And note 1 says where 125% of this current does not correspond to a standard rating of a fuse or non-adjustable circuit breaker, a higher rating that does not exceed the next higher standard rating shall be permitted. So I can go to the next, and remember, the next standard rating is going to be based upon the table. So if I do the multiplications, 125% times 208 is 260 amps. If I look at my table 240.6a, that tells me my next standard size higher than 260 is 300. So I could put a 300 amp panel board on the secondary of a 75 kVA transformer. Now, I talked to one engineer who told me, Tom, you don't ever do that because the full load amps on the secondary of this transformer is 208 amps. You wouldn't put anything more than a 200 amp panel board on the secondary of this transformer because your full load amps is 200 amps. Well, in reality, I can put up to a 300 amp panel board. And then the comment I got back was, well, what happens when you exceed that 200 amp full load amps? It's not going to exceed it. It could exceed that full load amps. I will just heat that transformer more. So if I put a 250 amp primary breaker on and I put a 300 amp panel board with a 300 amp main, I could load this puppy up. There's nothing in the National Electrical Code that tells me I have to size my transformer to the load. There's nothing in the National Electrical Code that tells me that. So I could take this transformer and really push it hard, which would add to the heating and could possibly reduce the life of that transformer, but I would still be following the National Electrical Code minimum requirements for safety if I used a 300 amp panel board on this application. Now, the secondary panel could be a 300. Typically, again, I say a 200 amp or a 225 amp panel board. I've had another engineer tell me that he would typically see a 225 amp panel board on the secondary of this 75 kVA transformer. Very common transformer to use. But based upon National Electrical Code requirements, I could put something much larger. Now, for sizing the conductors, this is really simple. If you've picked your overcurrent protective devices based upon inrush current, based upon selective coordination needs, based upon your incident energy needs, etc., the primary overcurrent protective device is going to be the size of the primary conductor is going to be the size of the primary overcurrent protective device. So if you picked a 225 amp breaker, you're putting 225 amps worth of conductor, even though you only have a full load amps of 90.2. If you picked a 100 amp breaker, or fuse, then you're going to put 100 amps worth of conductor, regardless of what the full load amps is. All right. So your conductor is going to be driven by whatever circuit breaker or fuse you picked on the primary of that transformer. For the secondary, again, conductor 2, if, again, I can put a 300 amp panel board. I could also put a 100 amp panel board. I could put a 150 amp panel board. I could put a 200 amp panel board. I can select anything less than 300 amps, and my conductor size is going to be based typically on the size of my overcurrent. Now, I could put a 200 amp panel board in there and put 300 amps worth of conductors. That limiting factor is going to be what the lugs can handle on your main breaker. So I can put a larger conductor than what I need, maybe for future expansion use if I want to, but typically that panel board, in my experience, that panel board's typically been right next to the transformer in many cases. So if I'm going to change that panel board out, I'm just going to pull a new conductor in the conduit. Even if I have to change the conduit, it's not a big deal. So in any case, I've gone through the primary and secondary breakers, primary and secondary conductors, piece of cake. We referenced a couple code sections in this 15-20 minutes, and next we have to make sure that we pick the right overcurrent protective ratings from an interrupting rating perspective. I leverage the infinite bus calculation. There's my equation that you take the full load amps over your percent impedance times 100, so it's 208.2 secondary, 5.06 times 0.9, and the reason I did 0.9, I didn't do this last time. I added 0.9 in there because that nameplate value, based upon the standards when we build transformers, I'm allowed plus or minus 10%. So I would multiply that by, or divide that number by 0.9 to compensate for that 10%, multiply all of that by 100, and I get a maximum possible fault current you could possibly see, assuming the low end of the impedance on that transformer of 4,571.8 amps. So, and if I look at IEEE 1584 tells me that my minimum, the number that they use, and I believe I had it open. Yeah, I do. It's right here. So section 4.3 of IEEE 1584 2018 tells us that sustainable arcs are possible, but less likely in three-phase systems operating at 240 volts nominal or less with an available short circuit current of less than 2,000 amps. Our available short circuit current at the secondary maximum is 4,571.8 amps. In some cases, you might have where you add conductor, or you add a source of available fault current on the primary of this transformer that may be less and less than an infinite bus, which it probably will be. It may impact your secondary available fault current a little bit. I doubt you're going to get down below 2,000 amps. So unless you add conductor run. So you could still have an arc flash, a likelihood of an arc flash event. So in my suggestion, again, use the arc reduction maintenance switch on the primary overcurrent protective device, make an electronic trip unit to give you that knee and short time to delay to ride over top of that instantaneous or that inrush current. And that is a 75 kVA transformer, primary and secondary conductors, primary and secondary overcurrent protective devices, not necessarily in that order. And we talked a little bit about incident energy, and we did it in a little bit more than 15 minutes. I'm going to hit that 15 minutes. At some point, I'm going to hit the 15 minutes. All right. I don't know if anybody even joined me live. Where's my... I got to find my... There it is. Anyway, so we have, Nihad. Nihad's out there. Steve Froming, happy Friday, happy hour. You know what I'm going to do after this? I'm going upstairs. I might have to cut the grass. I don't know. But I'm going to have a beer tonight. I am definitely going to have a beer tonight. So happy Friday, happy hour. And hey, Nihad, thank you. All is well on my end, buddy. I appreciate both of you guys stopping in. You know, I went live on Facebook too. Hey, Robert E. Thomas, and he is watching. Robert in the house, y'all. Thank you very much, Robert, for joining in on Facebook. Thank you very much. Hopefully, you guys got something out of this little short 15-minute tech talk. That's all I had, unless there's any questions. I'm just going. I don't see anybody with questions. Enjoy a beer on me, and have a good weekend. Stay safe and stay healthy. And Mr. Froming, keep doing what you're doing. I appreciate it. You too, Nihad, and you too, Mr. Robert Thomas. All right, everybody. I am going to give you back the rest of your day. So this little 15-minute tech talk went a little bit longer. But don't forget to subscribe. Hit the thumbs up even after you're reviewing this. Hit the bell when you subscribe. That way you'll know I'm online. I don't have the way to, share my Facebook and my LinkedIn site as well. I didn't put this on LinkedIn. I got to put it on LinkedIn. So I'll throw this up on LinkedIn as well. But please don't forget to subscribe. And I will be doing more of these 15-minute tech talks. If you have an idea for something you think I can get done in 15 minutes, send me an idea. I'll tell you what my lineup looks like. Here's the ideas I have. I'm going to do a 112.5 kVA transformer. I figure, I'll hit, and a 300 kVA transformer. I'm going to do a 15-minute session on the differences between AFCI branch, feeder, and combination type AFCIs. So I'm going to hit that. I just had a question last night actually, asking about that ground fault protection, GFPE inside of an AFCI breaker, whether or not, why some have them, why some don't. And I think I'm going to do one on the time current characteristic curve. I think I can probably nail 15 minutes on the TCC curve and taking a look at some breaker curves and fuse curves and help you understand how to look at them and what are the key areas to look at and what they're telling you. So the TCC curve is a very important piece of the puzzle. So if you have ideas on things that you say, hey, I'd love to know about this or that, let me know. I'll be more than happy to do some homework and some research and do a program for you. All right, everybody. Thank you. Thanks for joining in. And I am going to stop streaming. I have a button right here that says end. I'm going to do that, and it's going to stop streaming. So thanks. Take care. Stay safe and stay healthy.